And thank you for attending today's webinar on what's new in MSC Apex Jaguar. So if you haven't met me before, my name is Mitch Muncy. I am the product manager for Apex, and I will be your host for today's session. So since this is my first time doing a presentation for Apex, I just wanted to take a little bit of a minute and give a little bit of background on myself, and I'll introduce our presenter as well. And then we're going to talk about the new capabilities that we have in the Jaguar release. And then finally, at the end, we'll have save some time for a good question and answer session. And so please, if you have any questions during the broadcast, send them away. All right, so about me, so I'm based in Southern California. I work out of the MSC headquarters in Newport Beach. I started my career at MSC about 20 years ago before moving to a small local simulation software company. And so that company got acquired by a bigger one. I transitioned into a formal role with product management. And so far, coming back to MSC, working as a product manager has been fantastic. The team and the product and everything has been a great fit. So I know I've spoken with quite a few customers so far, and if I haven't spoken to you, I apologize. But I definitely look forward to hearing from you, getting some great feedback about how you're using the product, where you'd like to see it go in the future. And that's my email address. So if you have any questions, feel free to reach out. Just drop me an email, introduce yourself, tell me a bit about your simulation journey, or how things are going with Apex. I definitely want to hear from you. With me today is Steph Evans from Evotech. Evotech is a great partner in MSC based for MSC based in the UK. So Steph, why don't you give us a quick introduction?
Okay, thank you, Mitch. Can you hear me clearly?
Yes.
Great, thank you. Hello, everybody. Thank you for joining us on the webinar today. So a little bit of background about myself. I've got about 20 years or so of experience in specifically in FEA, mainly gained in the aerospace industry. I'm a chartered mechanical engineer in the UK, and I hold NAFEM's professional simulation engineer status at advanced level. I work with MSC in the UK as a business partner and do a lot of consulting and training, specifically in Apex, and have developed a number of classroom and online Apex training products. And if you're interested in looking at those in more detail, hit me up on the address that you can see on screen now. Okay, thank you. I'll hand you back to Mitch.
Yeah, so if you haven't seen it already, like Steph mentioned, he's put together some really nice comprehensive training content for Apex. If you're new or if you want to leverage some more of the advanced topics or just brush up on some of the new functionality, like the things that we're covering today, I definitely recommend checking that out. So in case you haven't seen it, I want to take just a minute and highlight our recently published white paper. So it's an interesting read, if you mind. Yeah. But it doesn't really focus on product functionality as much. It really is introduction to the background of the vision and the strategy and where we see the technology going in the future. So, in the context of today's webinar, I just want to take a few minutes and highlight a few of these topics so you can see, the new features as they come out, exactly how they're aligning with what we've been thinking. So to start, we'll start with unified. And for me, unified means having a consistent look and feel throughout the product. So the tools, the applications, and how all the data is connected. So this consistency is what makes the product easy to use and help cut back on training for learning and relearning. Representative means that data is centralized and reused where appropriate. So this means being able to filter our interface and our data according to the context and exactly what you're trying to accomplish with the product. Parametric means design changes are reflected throughout the entire simulation process. This allows for quickly evaluating what-if studies or new designs. I think many of you have already taken advantage of this. Innovative is trying to think and rethink how simulation is done to improve your productivity and reduce headaches. Apex has already received a number of recognitions for doing just that. Automated is the process of taking all this amazing functionality and scripting so you can focus on the valuable part of your day. This reduces error and unlocks workflows that might be time-consuming or difficult. So definitely check that out if you get a chance. MSC Apex is a great product and a great place, and I'm excited to be working with Steph today to show you some of the new features we have in Jaguar. So with that, I'll hand it over to Steph.
Okay, thank you, Mitch. Let's get started. Okay. So, yeah, as Mitch mentioned, we'll be covering a number of new capabilities and features in the Apex Jaguar release. I'm sure many of you are familiar with Apex in terms of its development journey. Some of you may be new to Apex specifically for this Jaguar release. So we've got a number of exciting capabilities and features in Jaguar. We're going to focus on three key areas today. First of all, we're going to be looking at the Apex MSC Nastran Interoperability. So we've got a lot of enhancements in Jaguar. We've got better import-export and ability to look at results generated outside of the Nastran environment, outside the Apex environment. We've got a new concept, we're calling this abstraction, which allows us to tie Apex models and Nastran models together more closely, and we'll see examples of that. We've got enhanced assembly management and load transfer with something called mesh-independent ties, which we'll look at. We've got enhancements in many other areas, looking specifically at coordinate frame definition and control. And then, of course, as Mitch mentioned, we have a rich set of Python automation or API enhancements in Apex, and some of those functionalities are very new in the excuse me, in the Jaguar release. We're going to move on to look at the second workflow, a second set of enhancements that's key in the Apex in the Jaguar release. So geometry, meshing, and view enhancements. So we've got enhanced control, checking, and exports for geometry and all different types of meshing. We can, and this is very key to many of the workflows that people are looking at in the contemporary sense, look at the ability to generate, modify, reuse or remesh faceted and real NURBS geometry from legacy FEA models. So we'll talk about all of these features in a little bit more detail in a moment. We've got enhancements. We can now create images and record movies directly in the Apex environment. And we've also got a multi-view results exploration environment in there as well to compare different results, different events, and different models. And then the third area we're going to touch on is something which is completely new to the Jaguar release. So this is the ability to interface MSC Adams output in the Apex environment. And through some of the marketing that we've been doing and the feedback we've had, this is an area that lots of people are very interested in, and opens up a new realm to some of the Apex capability. So specifically through a series of example videos we can look at how we would access Adams Car models and the results data derived from those models. We can then associate real-world geometry, so real-world CAD assemblies of given vehicles, and the ability to interrogate those results linked to the real-world geometry. And then finally, we've got the ability to map loading derived from the Adams multi-body dynamics simulation onto the structural FEA model in a single environment, which gives us a very nice and clear workflow. Okay, so moving on, we'll look at the first workflow. So again, touching on the Apex to Nastran interoperability. So we've had a lot of capability for this for some time with various different Apex releases. But now, specifically, we've got, as I mentioned, the ability to work with external data, importing, export, and looking at MSC Nastran results. So we've got more capability and more model scenarios and other scenarios covered now with the ability to round trip. So we can read in many more Nastran keywords and concepts for that matter, and we can export those same keywords and concepts as well. So giving us a much more rich workflow in terms of Apex for dedicated MSC Nastran support. We've got a much more streamlined results access. So we're using the contemporary Nastran HDF5 binary result file format. So we've got enhancement to the way that we can support those results from models that potentially were not generated from Apex, maybe legacy models, that kind of thing. We'll look at a new concept, which is pretty powerful, really, in terms of Apex usage, discrete MSC Nastran usage, and also the integration of those two different tool sets. So we have some new keywords, abstract keywords, abstract naming and abstract entities, which you can see here. Obviously, these will be added to the Nastran reference guide and documentation for the Nastran users, because again, this is new for Nastran as well as Apex. What this allows us to do is to define multiple MSC Nastran abstractions to support the way that we work within Apex. So things like connectors, beam spans, remotes, loads of boundary conditions, etc., which historically may have taken multiple keywords in the Nastran environment, we can now group using this abstraction concept, which means that we've got no data loss between an Apex model build, the exported Nastran model, and vice versa. So a Nastran deck with abstractions can now be read into the Apex environment, and those entities are respected. So we're going to look at a quick example here. So I've just taken something which is maybe pretty familiar to lots of people, a connector example. So a legacy method here may be to tie two discrete meshed entities together, maybe with a couple of RBE type elements, a couple of grids, and then a C-bar element to make up the full definition for that connector. And then if we look at the Nastran keyword, if you were to pick these out in your quick reference guide, you would see that you need all the information for those discrete entities. C-bar, grid card, and RBE3. So the introduction of abstraction in both the Apex and the Nastran world allows us to collect all of these entities together and group them into a single abstracted entity. And this has key benefits and key influences in terms of the way that we work with those Apex models. And then we've got the keywords here, may look a little unfamiliar to those who have not seen it before, but basically we have an abstract naming convention, so the ABS NMVS name, which assigns an ID to a text string. And then we have the abstract cards, which groups those legacy Nastran keywords, the C-bar, the grid, and the RB3, into a single abstract definition. So here we're using the name, 02 spar brackets, blah, 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 and assigning that to an abstraction ID of 1503. We'll just look at that in a quick video example. So we've got some recordings of work that I've been developing, and we're just going to run through a couple of examples of how these new functionalities work within the Apex environment. So we're just going to look at some of the model import and export round tripping. So we're reading in an externally generated or a legacy FEA model, and we can see some of the keywords that Apex has spotted. So we've got the abstract cards, we've got some mesh independent tie cards in there, and then we've got standard things like grid, material, and property and element information. We can look through the data table to see what's going to come in if anything's been skipped. Obviously, set the unit system and how we want to organize the model browser based on this model import. So just import the legacy model, and we call this an orphan mesh because there's no geometry in the model. So Apex is much more capable now in terms of working with orphan mesh models, both in terms of this round tripping and also in terms of some of the geometry creation and remeshing that we'll look at in the second workflow. But we can see that the majority of those keywords have been brought in. There's a couple that haven't, but they're stored in the bulk data entry for model export. So there's no data loss in terms of this model definition. So we just got a standard wing model here. Many of you aerospace folks may be familiar with this type of thing. And we've got a local area where we have some detailed mesh definition, and we can look through the model browser and see how the Apex model has, or rather the Nastran model has been redefined in the Apex environment. So very clear model browser in terms of handling all of those objects within the Apex environment. We're looking at glue contact, or what we now call the mesh independent tie. We can see that's been read in. So that's a new functionality in terms of the Apex environment. So we're using these mesh independent ties to tie the local detail into the larger wing model and within the discrete parts within the detailed region. We're just cycling through some of the connectors. So we've got multiple R-bar entries for the Nastran literate amongst us. And then we've got the standard connector types. So we're just going to highlight in the model browser and show only those connected types. And we can see the clear Apex definition or visualization for those connectors. So we've got node-to-node connections and multiple node connections through MPC type definitions. So we can double click on any fastener within the model browser and then understand the properties of that given fastener. This is pretty standard really in terms of Apex usage. But the key thing here is that we're looking at one particular fastener, which is made up of the C-bar and the RBE type elements that we were talking about in terms of the Apex abstract, sorry, the Nastran abstraction. So we can look for the abstraction cards. So we're looking at the ABS naming card and then the abstract card. So we can cycle those through the Nastran input deck, and we can see how those work for things like constraints, beam spans, and connections. And then just looking at one area of local detail. So we're going to type in, or rather copy paste in, the name of the connector from the Apex model definition. This is from the Sparta brackets. So if we search for that name, we find the abstract naming convention. So the 1503 ID that I was talking about. And then if we then paste that ID and search for it elsewhere in the model deck, we've got the abstract cards, which indeed group those abstraction types together. So you can see here C-bar, grid, and RBE3. So because the model was defined with this abstraction methodology or concept, when that model was then read into the Apex environment, we've got much more integration with the Apex and the Nastran model definition. So Apex hasn't broken it down into lots of different entities. We've got much more streamlined HDF5 results access. So we just create a scenario, import Nastran results, set the unit system, and bring the results in. So these results are generated by an external Nastran run and could have certainly been run without any involvement of Apex in the past. So once we've got that HDF5 attached, we can then go into the post-processing mode and see the discrete events or cases on the left-hand side of the model, and we can cycle through. And indeed, now we can write results, filter results, sort results, and then export this data to external means. Okay, so that's looking at round tripping, keyword support, and abstraction. Just a couple more things I want to talk about from the Apex Nastran Interoperability perspective. We've now got, again, the enhanced assembly management and load transfer control with what we call mesh-independent ties. So those of you who are familiar with Apex previously, the term glue has been replaced with mesh-independent tie. We do have some real glue functionality coming out in the future, but to avoid confusion, we've changed that glue terminology. And we've also updated or enhanced the way that mesh-independent tie works. So we can now specify user-defined regions which are tied together, as well as the full body definition. So prior to Jaguar, you had to glue the full contact face between two bodies. We can now connect remote regions as well, and we'll see this in a video example. Okay, so we've got this going back to this detailed wing region. So if we just look at that on its own, and we've got a mix here of different components. So we've got spars and skins and ribs and some local bracket detail. If we look at the mesh-independent tie that's tying those discrete regions together, we can see that at the moment the tie is defined across the full interface of any given contact pair. So, for example, we've got the lower skin tied completely to the spar flange, and the upper skin tied completely to the spar flange. We're looking at discrete fastener modeling as well. So we don't want to double up on having glue contact where we've got fasteners. So we're just going to edit the tie definition. So we can see here we've got the full body defined, and we're just going to define now a local region. So pick an element and connect, populate those with the elements connected. and then we update. So now that tie is just the local area on one side of the interface. I'm just going to repeat that for the second side. So at the moment, this left-hand side, or it depends how you look at it, but this side of the model needs updating. So we're basically breaking out the mesh-independent tie to not be defined over the full interface between those two regions. And if we just jump a few steps here and then look at the connectors, we can see now that we've changed those tie definitions. So we've basically taken out the glue from the portion where the fasteners exist, and then we can verify the model, or we can run all case, or we can export for Nastran analysis. Okay, so moving on, we've got enhanced coordinate frame definition and control. So one thing that's been added to Jaguar is now support for the reference and the displacement coordinate frame, which each grid represents. So the reference frame defines where a grid is in space, and then the displacement frame defines in what direction results or components of results are displayed within. We've also got now the ability to look at beam element coordinate frames, and then we can modify those frames and update them very easily on the fly. So we've got a quick example of this. So we've got a simple 2-bracket assembly. We've got a number of different coordinate frames that have been imported. Again, this is a legacy model that's been pulled in from an external Nastran source. We could easily build this in the Apex environment. So if we take out or look at each part individually, click on the parts, and we can see the coordinate frame that's referenced by those parts. So the blue bracket has a different reference coordinate frame to the pink bracket. And then we can run the analysis and post-process. Okay, but what we're going to look at now is the impact of changing the position or orientation of the reference coordinate frame. So if we show for the pink bracket, which references coordinate frame 1, which is shown on the screen now, we can double click on that frame, and then using the triad, which is familiar with many Apex functions, so we can rotate this coordinate frame by 45 degrees, and as soon as we press enter or the red mouse button to accept, the position of that pink bracket is now updated purely by moving the reference coordinate frame or changing the orientation of the coordinate frame. A very, very straightforward way of working and far more efficient over legacy methods in other tool sets that we may be familiar with. Okay, so we've moved the position. So we now run the model. What we're seeing now is the multi-view aspect of Apex, and we can look at the results for both different models. So the reference frame is updated, and then the X component is updated for the results output as well. Looking at beam coordinates and the coordinate frame definition, so we can now visualize both the shell and the beam coordinate frame. So some display updates here, so we can change the picking filters and show the beams and the frames that are referenced by those beams, and then the shells in the same manner. Okay. So if this was a real-world example and somebody was interested in the joint loading developed at the interface, you might wish to change maybe the shell orientation to be aligned with the bar element orientation at a given location. So the x-axis for the shells is currently pointing to the left. We're going to modify that now so it points down to the vertically downwards in the same orientation as the bar elements or the beam elements that are connected to the structure. Okay, so just tying up those. So it's just a means of improving the display and the control of the model. Okay, we're going to look at a couple of API enhancements. So there's a lot of stuff that can be done from this perspective. One key thing within Jaguar is that we can now support a lot of the composites functionality from both from a build and a post-processing perspective. And we're going to now look at a simple example of layout generation and look at how those macros or those API enhanced tools can be accessed via the custom tool palette. So looking here at a fuselage panel, so just a curved composite panel with stiffeners, and we can go through. So we've got a standard panel build, and we can check the ply layup on those for that given panel. We can use the core sampling tool to pick an individual element and see the layup. So this is color coded based on orientation. And then we can check the thickness of the laminate. So this is standard Apex usage. This particular function isn't really new within the Jaguar environment. I just wanted to show you how you would work initially defining a composite panel, and then how you can update the laminate for a given region based on some API or macro tools that have been developed. Okay, so I'll mention that I've had some assistance from a colleague in the UK for MSC, Andy Main, who's been very helpful with providing the macros for this. So thank you to Andy for that. So yes, now looking at the ply-based response. So we're looking at the failure indices for a given panel. Obviously, we've got the relative scaling turned on. So we just scale that down a little bit to make a bit more sense. So we can assess the results as we wish. Let's assume that we've exceeded a design criteria, or we've seen a failure index greater than 1 in a particular region. So we're going to now look at updating this composite part definition. First of all, by modifying the geometry and the mesh in the generative manner. So we've just created some geometry that fills this window hole. We've extruded that out in 2 directions. And now we're going to use the split tool. And again, split using an offset face. And this is a new enhancement in Apex. Then we can pick curved faces, pick contiguous edges, and then define an offset dimension or distance. And we're going to break out the panel at a distance of 100 mil from the picture frame. Okay, so generative update. So the laminate and the mesh is all updated as we wish. So we're now going to look at using the composite API tool. So rather than building a panel in the manual sense, we can simply use this add ply stack macro, where we can specify the ply angles, the thickness of the plies, the material, populate that. So we're defining an 8 ply stack on this picture frame. Check the green tick, and the model is updated. We get a log file which shows us the laminate, again with those materials, angles, and thicknesses shown nice and clearly. And of course, that updates the underlying panel, the composite panel within the model browser. So we could go back in and check that if necessary. So we've defined the thickness as we wish. One nice aspect of this add stack tool is we can drop plies on top of one another. So we've repeated this a couple of times, and we've now got 8 plies acting as a sort of a local support for the perimeter of the window. Cycle through those with the core stack tool. We'll look at the 2 discrete regions. So we've got 12 around the window and 8 plies for the rest of the panel, and then run through the analysis, and again look at the discrete ply output for each ply within the model. And we can cycle those through and look at layers 1 through 12. So obviously when we get to the plies 9, 10, and 11, we only see those plies for the local region that's had the reinforcement defined. Okay, so looking at those results, and we'll see, yeah, again, looking at the multi-view capability within Apex, we can look at the new and the original model results side by side. So pretty useful for results interrogation. Okay, so moving on to the second workflow, and then we're going through a lot of stuff pretty quickly here. So if you've got any questions, please put them in the Q&A, and we can address those as required. So some of the enhancements now for geometry meshing and viewing. So we've got a number of things that we can look at. So first of all, we've got considerable geometry manipulation enhancement. So we'll look at some of this detail through the video shortly. We've got mesh manipulation, and we've also got the ability, or we've got enhanced model checking, and we can now export to step and IGES. Previously, we could only export to Parasolid. So if you're limited to your maybe your CAD system import options, we've got more export capability to suit you. Okay, so we're looking at part replace first of all. And this is a new concept in Apex. So imagine we've got a part that's been meshed and tied into an assembly. We can simply right-click on that part, select a new geometry definition, and Apex will interrogate that information. See the model browser update shortly when the interrogation is completed, and it will effectively map all of the mesh, the connector, all of the essentially materials and properties from one geometry definition onto another. And then we can show the old and the new part just by turning the tick boxes on and off. And then when we leave that form, the model is updated. We've got the concept of parametric primitives, pretty straightforward, but these are basically things like box, cylinders, spheres, and ellipsoids, which we can now drop into the model without having to go through sketch and extrude and that type of thing, but basically drop them onto a model, and they're pretty useful for, example I'm looking at here, for global local mesh transitioning. So we've just taken that primitive of a cube and done some Boolean operations and then defined some cells in this overall solid. And we can then define the detailed region with a given element edge length, and then the rest of the model with a more coarse element edge length. So really quickly way of transitioning meshes through the hybrid meshing techniques. We've now got enhanced splitting tools. So we saw this with the fuselage frame example, but we can basically now pick a surface and then offset from that surface. So here, some pretty simple geometry manipulation, but if you wanted to define maybe different properties around the cylindrical border of a fastener, you could now offset and then partition the geometry. Enhancements to the incremental surface meshing functionality. So we can update the local controls, the local dimensions of a particular feature, and then we can copy those features from one entity to the next using the clipboard type approach. So we can basically design our feature mesh before we go into the larger surface mesh definition. We've got mesh control enhancements, mesh curve control, I should say. So we can now associate curves onto much more complex geometry, and the mesh is updated accordingly. We're not splitting the geometry, the surface geometry here. We're merely associating those curves. So if we had a pressure defined, then we wouldn't need to update those pressures at the cut. And again, looking at the multi-view, we can see how we very quickly updated that model definition. We've got enhancements in terms of 2 and 3D element quality checks, so we can turn on which checks we're interested in through a tabular tick box form, and then we can zoom in on particular poorly shaped elements. We can grow the mesh for 3D elements, which is new for Jaguar. We could do that with 2D previously, and then we've got the ability to export step and IGES direct out to whichever environment you're interested in. Okay, so again, running through this stuff pretty quickly, but we're trying to get through a lot in a pretty short frame of time. So we're looking now at the ability to generate, modify, reuse mesh and NURBS geometry from legacy FEA models. So this can be very useful for a technique that we call facet body smoothing, which will generate 2D and 3D geometry from literally any mesh definition. And then we've got the ability to create real geometry in the NURBS form from more feature-based CAD definition. And we've got a quick example of this. So you may have seen this on LinkedIn. I put a LinkedIn video out on this a couple of days ago. So we've read in an orphan solid tech mesh, and we're using the geometry from mesh tools to create a faceted body from that underlying mesh. And that faceted body can then be remeshed or modified as necessary. So it's a two-step process. We go around looking at key features, and if we spot an area that does need updating based on tolerance, so we've got the compound fillet here. So we're going to split up some of these colored zones to give us a better feature definition, breaking those up so that we've got the 3 fillets working together. So once we've broken up those features in the manner that we want, we can then tie discrete faceted surfaces back together. Okay, so where we've got color mismatches here, we can just join those surfaces to reflect the features in a much better manner. Okay, a whole host of different ways of working with this kind of legacy mesh. It could even be scan data mesh geometry to rebuild the CAD geometry from. And once we've created those features, we can then make sure, using this color coding, so flat faces are in blue, fillets in red, toruses or tori are in purple. And then we accept that, and then in the model browser on the left-hand side, we can then show the geometry that's been created from that facet body smoothing. Okay, and again, this will work for literally any geometry, no matter how complex it is, based on the facet algorithms. Okay, we can delete the mesh, and potentially we can remesh. We could use some of the hybrid mesh transition techniques that we saw in the last video, where we broke out a solid region of interest. Okay, now we're going to look at geometry from mesh for NURBS. So if you're not familiar, NURBS stands for non-uniform rational B-spline. It's a fancy way of saying nice, clean, editable geometry. Okay, so similar process. Pick the legacy mesh. So whether this is a legacy FEA model or coming in from scan data or what have you, we can then use the algorithm to pick out the features. So we can modify those as necessary again here. On this form on the right-hand side, we've got a simple checkbox that basically says, do we want to create faceted geometry and or NURBS geometry? So here we've done this for solid geometry. So one benefit now that we have with real solid geometry over faceted geometry is that we've now got much more control in terms of the maybe defeaturing and mid-surfacing and stuff. Okay, so we're just taking some of these fillets out of the model and cleaning the model up, running through some mid-surfacing, pretty standard Apex functionality, but obviously the effort in getting to this geometry from a legacy FEA model would have been very difficult using legacy methods, pretty much impossible really. Okay, so we've got mid-surface defined. We can then defeature that mid-surface. We could have defeatured the holes from the original solid, but we're doing this so that we've got hard points or seed points at the center of the holes, and then we can remesh that geometry. The shell properties will have been retained as part of the mid-surfacing exercise, so we don't need to repropertize the model. And then we can show how that updated 2D and 3D mesh then sits within the assembly. So we've got the model definition here. One thing that will need updating is the original fasteners, and again, these were created using the Nastran abstraction technique. And we've got, again, thanks to another MSC colleague, Larry Pierce in the US, who's very helpful in defining a macro script, which can be used to update these broken connectors. So on the left-hand side, we can see the cross is showing where those connectors are broken. So we just run the macro, and it looks for the position of the fastener hardpoint from the shell mesh and rebuilds the fasteners. Okay, so absolutely trivial means of updating the model and massive efficiency gain here. Okay, so if you're familiar with legacy models, if you did want to do this, just take a moment to think about how long this would have taken using the your old processes. So huge gains to be had here. Okay, and then finally, just looking at the original tech mesh that we had from the legacy model, spin the model, and we can show the shell meshes that have been updated or created from the geometry, and then the fastener connectivity updated. So really powerful. Can't state that enough. Okay, we've also got enhancements to the image capture and multi-view environment. So we've got the ability to create JPEGs, PNG, bitmaps, I can't remember the full list, and many different movie types, so AVI, MP4, that type of thing, for dropping into presentations. So far more easy way to do those things. And we've also got the ability to look at results from a multi-view perspective, looking at different events and also different result types and also model configuration. So we can look at the results of two different models in the same database, and that's pretty useful for assessing the structural response of many of your parts. Okay, so the bracket that you looked at, or that we saw in the previous videos, just going to run through the analysis. So standard Apex functionality here. So we're running this using the embedded Apex solver, the Apex structure solver, I should say. So we're not doing a remote Nastran run. We could have done this remotely if necessary, but it doesn't really matter. And then we can look at the response of two different models. So on the left, we've got a very fine definition. On the right, we've got the original course model definition. Okay, so that's now available with multi-view. Okay, so moving on to the third workflow, or the third set of enhancements that we've got within Jaguar, and this is focused on the Apex Adams Interop. Okay, so we can now access the Adams Car model using the Adams Car database, so the CDB format model. We can display and interrogate the model definition, or the Adams Car model definition, within the Apex model browser in exactly the same manner that we would look at a standard FEA or structural model. And then we can import and then look at the results of the Adams Car analysis in the Apex environment. And there's a very, very useful, important technique that we can look at in a moment, showing how all this ties together with the structural FEA model. But just want to show a quick video of how this works just by bringing the Adams Car model and the results. So we would go to File, Import Adams Car Model, pick the model, the CDB file that we've got located somewhere. We see the functions run through as the model is translated into the Apex environment. And you'll see a very nice looking Ferrari. So we can spin the model. So we've got full model browser control in terms of visibility and interrogation. So I'm just going to change some of the colors here. Really trivial model updates here, but a Ferrari needs to be red. So we've just updated the paintwork, as it were. Centered in browser the windscreen and made that transparent as per some of the visibility you may need. We've got that in there. We can hide and show from the view space, so exactly the same way you would work with an FEA model. I'm sure there'll be some Adams users on the call, so that this is all very new for you now, and a very nice way of looking at your model and results. So we can look at the interface points. So these are the points built into the Adams Car model where loads are extracted from the analysis, and we look at the full set. So these are the key positions. There may be suspension interface points, steering positions, that type of thing. And then we can look at the full model as required. So we've now got a slightly different model here. This is brought in from an Adams Car database, and we're going to look at bringing in the Adams Car results. So we go into studies, and we've got a scenario set up that's pulling this convertible car model representation. And we've got a couple of events defined, and we can pick out the Adams Car.res files to bring those in. And we can pull those into the Adams environment, the Apex environment, and then go into post-processing. So this particular model has got the Adams Car defined and all the interface points and local coordinate frames set. We've also got the track that was used for the simulation, and then the full time history response for the car running around the track. Looks like a hedgehog at the moment, but we will improve that in a moment. So just running through that, showing the full transient behavior. And then we've got a couple of techniques where we can move what we call the dynamic camera. So we can basically datum a camera onto the car itself on a single location. And then when we play the output, the car doesn't move from that datum location, but we can see the impact of things like the suspension, movement and motion, and ultimately look at the forces, accelerations, displacements that are derived from that scenario. Okay, so we've got now the ability to look at the Adams car model imported, but we can also import external CAD geometry that may not have been in the Adams car environment, and then we can associate that model definition. In other words, we link that external CAD into the Apex environment and link it to the Adams car model. Okay. We can then interrogate the results for the regions of interest and specify the key time steps that we might wish to analyze in a downstream analysis. So ultimately, the workflow here is all about getting the Adams car data, interrogating it, visualizing it, and then using those loads to be mapped onto the structural FEA model. Okay? But just a quick video looking at the CAD model integration. So we're importing external CAD file. So we've got this Baja buggy, little bit of artistic license on some of this geometry, but you can see that it's pretty good in terms of the detail, certainly for the tubular space frame, the wheels, and some of the suspension members. We're going to be particularly interested with this workflow on the lower wishbone suspension for the front left wheel. So we can see the geometry overlaid over the Adams model. And once we've got that in position, we can then associate that model simply by right-clicking on the Adams model and linking the CAD geometry to that model. And then we can do this in an automated sense, but I'm just showing this in a manual sense first of all. So we're going to first of all manually link the wheel, or the brake disc to the wheel. So we link the wheel, the Adams model, to the real wheel in the CAD geometry. And we'll repeat the same for the wishbone, link that across. And as we link, the entities disappear. We can control if they disappear or not with the checkbox, but it gives us a good idea of how much of the model is mapped across. Okay, so we can repeat that to map the full model if necessary. In the model browser, we've got the model association visibility turned on. So when we show the Adams model, it's also showing the underlying CAD definition in there as well. So if I turn that on and off, it will bring the geometry in and out of the Adams model. Okay. We can now visualize that the output. We can look at the control arm on its own. So for example, we might wish to map the loading from the Adams wishbone through these interface points that we can see on screen now onto the real locations within the CAD definition. Okay. We're going to go into post-processing. And because we've linked the CAD is now visible in the post-processing environment. When we turn it on within the model browser, searching through for or rather showing only the interface points for the Adams representation. We'll assess these forces first of all before we look at the geometry overlaid. So we're looking now at the interface load, so the resultant force acting on the wishbone at any particular time within the Adams car analysis. We're just turning on the dynamic camera as we looked at previously, so that the wishbone doesn't move and only the force vectors are updated. So we can play an animation of how those forces are interfacing, or rather how that wishbone is interfacing with the rest of the structure. We can do this for components or full assemblies, and we can graph using the multi-view functionality, looking at the time history, so the forces as they get mapped across into the wishbone. So pretty useful in terms of interrogating that structural response. And then we can maximize the graph, and then based on those peak loads, so we're just showing the peak resultant forces acting on those 4 interface locations. We can then create data points as we wish at any one of those peaks. We could create as many of these data points as we wish, or we can delete them and redefine others, as shown on screen now. And then really the key thing here is the ability to take that information and perform the next step, which is the loads mapping onto the structural FEA model. Okay, so we first of all need to tie the Adams car interface points to the FEA model using some discrete ties. Then we're going to map the loads in a similar manner to how we map the geometry. And then we're going to analyze and post-process the FEA model. And then we've got a part replace exercise, similar to the example we looked at for the tech mesh bracket. So we can replace, or rather update the geometry very quickly and easily, and then use the multi-view output to assess multiple model configurations. Okay, so we've got the FEA model here now, which is developed from local assembly part definitions. So we've got tech meshed brackets or lugs, and then shell meshed tubular section. Could be a composite tube or what have you. So we're maybe looking at a design change. Pretty simplistic example, but illustrative of the overall workflow. So we're going to create some compliant ties. So for the Nastran Savvy, these are RBE3s, which connect the face of the geometry or the face of the mesh into the interface locations, so that we've got effectively a structural input point that the FEA model can be loaded up from the Adams Car results. So if you remember those data points that we created from looking at the graph, those four data points will be used to create 4 discrete events or 4 discrete load cases for performing the structural analysis. Okay. So just showing those discrete ties, and then we're now going to create another model association. So associating the model with the geometry, the car model with the geometry, and then the car model with the results at the interface locations. We just repeat that for the, so we're going to switch out the idealized wishbone from the Adams Car with the detailed FEA model that we built in Apex. So manually mapping, so pick the 2 entities. We had this set to make them disappear. We could have changed the visibility so that they stayed on screen, given the simplicity of this particular set of geometry. So we run through those, the process, and then it's a case of mapping the interface points from the Adams Car model to the Apex FEA model. Okay. So once we've done this, again, we've got those scenarios created, those events created. We can run in the Apex solver. We can run an external Nastran result. We can export the model neutral file back into Adams if required. So full set capabilities for the total workflow definition. Okay, so skipped over that pretty fast, but we've got the 4 events created as part of the load mapping exercise. So we can look at both the force and moment state, and then we can go into studies. So that mapping has created a quasi-static scenario with those. Actually, I keep saying 4 events. There's 5 events it's created, and we can look at the load boundary condition definition, and then see how the representations of force are given for different time steps that go back all the way to that graph that we defined. And then we can run the model. We've got inertia relief set on, so we don't need an explicit set of constraints. So the model is sort of free with the free body loads applied. And then we can post-process the model and see response going into the multi-view environment. Post-processing, so we can compare the Adams model with the deformed plot for a given load case, and we can create viewports for each discrete load case if necessary. So just looking at those different output events. You can see the 5 cases. So we've got the relative displacement set pretty high. Obviously, the wishbone wouldn't move this much in the true assembly. So we can create a viewport for each one of those events. We can turn off the Adams model. So we've got multiple cases shown at the same time. So super fast way of interrogating the results. And think back to your legacy toolsets, guys, and it would have been pretty painful to do with the old methods. Okay, we can look at hotspots and fringe plots and all that good stuff from a post-processing perspective. And then we can look at part replace. So here we've just simply used part replace. So this this middle bracket where we've got 3 tubes coming together. We may have had a stress hotspot or some fatigue issue there. So we've just looked at some updated geometry and used part replace to update the model. So we, again, using the generative nature of Apex, we haven't had to define anything in terms of the model build. So the meshing, the loads and boundary conditions, the properties, the contact, all of that has been updated in a super fast manner based on that functionality. Okay, so went through quite a lot there. My voice is probably getting a bit hoarse. Just to summarize, so we've looked at some of the Apex Nastran Interoperability. We've looked at geometry meshing and view enhancements, and we've looked finally at the MSC Adams Interoperability. So I'd now like to open this back up to Mitch. Are you there, Mitch?
Yeah, I'm still here. So thanks, Steph. I know we added quite a bit of functionality with this release, and so covering it all in the time allotted is going to be a challenge, but that was perfect. So thank you very much for that.
Okay, thank you, Mitch.